Hello, thank you all for coming today. So, today we're going to be looking at how to use Python with physics, and specifically how Python can be used to solve the sorts of problems you're going to be encountering in physics, and how you can do that sorts of problem solving. And to do this, we're just going to look over a pretty simple ramp motion problem, which I'm sure all of you are very familiar with and could solve on yourselves on paper. But really, the point of this is just to demonstrate the use that it has. So the problem we're going to be solving here is a simple ramp motion problem, as I said. And this one asks us to find the parallel component of the displacement for a box of mass 0.5 kilograms sliding down a ramp of angle 30 degrees with a frictional constant of 0.1. And so we're just going to be going through this problem and kind of solving it together. And so here we have our diagram, and we just drew in our free body diagram with our three forces that are acting on the object. We have the normal force, which is perpendicular up from the ramp. We have our frictional force, which is parallel to the ramp, pointing opposite the direction of motion. And then we have the force of gravity, which as always is pointing directly down. And then we're just going to start with our simple position function, which is d parallel is equal to the initial parallel t plus 1/2 a parallel t squared. And I just use the equal symbol for those little parallel lines right there. But of course, obviously, right away, we can take out v initial t because v initial is 0 in this particular instance. So that is not of consequence to us. And so what we end up with then is d is equal to 1/2 at squared. And we need to find what a is. And how do we do that? Well, we go to Newton's second law, of course, which is F net is equal to ma. And in this particular instance, we have two forces that are acting in the parallel plane to the ramp. We have the force of friction, which is pointing in the opposite direction. And then we have the parallel component of gravity. And so we have F net parallel is equal to Fg parallel minus the force of friction, with down the ramp, of course, being the positive direction in this particular instance. We can then go ahead and substitute that in, and we have Fg parallel minus the force of friction is equal to ma. Now we're just going to move on to part 2 here and rewrite what we already had. Next thing, we're going to substitute out for Fg parallel, which is equal to Fg sine theta, and that theta being 30 degrees of the ramp. And then you substitute that back in, of course, and we have Fg sine theta minus the force of friction is equal to ma. Next, we're going to do both of these at once just to kind of get it out of the way with. We have Fg is equal to mg, and the force of friction is equal to mu Fn. And then we have mg sine theta minus mu Fn is equal to ma. Once again, just rewriting what we had for part 3 here. And then next what we can do is we can just go ahead and substitute out Fn to be equal to Fg perpendicular, which once again, Fg perpendicular is equal to mg cosine theta. I just went ahead and skipped the step of substituting out Fg there because we've already seen that happen before. There's no point in repeating it. All right, and then if we rewrite again, that's mg sine theta minus mu mg cosine theta is equal to ma. Just some quick algebra steps. Mg sine theta minus mu cosine theta is equal to ma. Divide by m, and you have a. And then we finally have our value for the acceleration. And we can substitute that in to find our final equation, which is equal to d is equal to 1/2 g times quantity sine theta minus mu cosine theta t squared. And we can put in any value for t, of course, and find the displacement after that time has elapsed. So that was a pretty simple problem, I'm sure you'll find. And there's a lot more complicated ones I could pick, but I'm just trying to figure out something that y'all might be familiar with here. But what we're going to do from here, though, is we are going to then take this work that we just did, and we're going to go through how you can translate that into Python script, which will often be more efficient and get you a lot more information. All right, welcome back, and we are now here in the Python notebook on Jupyter. Jupyter is an application that you can download onto your computer off just the internet. It uses your computer's memory to run the code. However, it is just hosted on your browser. It's not actually web-based. You still need to download it and everything. Fortunately, however, it is free and it is very useful. And what we're going to be doing here is basically running through that problem that we just solved out on paper. However, this time we are going to be translating all of that into Python code. And something to note, I believe, before we finish is that Python, unfortunately, does not solve all your problems. You still need to understand the code. You still need to solve all of the problems. What Python enables you to do, however, is it enables you to do a lot more calculations a lot quicker, and it can give you more information than you might be able to on hand. And we're going to see that here in a minute. But you still need to understand what's going on, and you still need to be able to solve the problems. All right, so to start with, what we're going to want to do is we're going to import the functions that we need from the math library. Basically, what that means is that Python itself comes with a lot of obviously basic math operators like multiplication, division, exponentiation, addition, all loaded onto it automatically. However, what it doesn't have, just to start with, is more complicated things like trigonometry, calculus. Fortunately, those can be downloaded from Python libraries, which can be found just on the internet. And the one that we're going to be using today is the math library. Jupyter comes with the math library as well as several other libraries already loaded onto it. So when you download Jupyter, it just already has those. And so we're going to say from math, which is the name of the library, import cosine, sine, and pi. Okay, and then we are now going to define our variables. Variables are basically strings of letters, numbers, whatever, that are set equal to some value. And they pretty much work exactly as variables do in math, only they're not necessarily limited to numbers, of course. But for our purposes today, they will more or less be numbers. And we're going to start with g is equal to a gravitational constant, 9.8. Then we're going to set the mass, m is equal to 0.5 kilograms, which is given in the problem. And mu, because unfortunately I don't have Greek numbers on this keyboard, is going to be equal to 0.1, also given in the problem. And then theta is equal to 30. However, what we need to note here is that in the math library, cosine and sine both function with radians, not degrees. So if we want to use those with degrees, we need to reassign our angle theta. And how we're going to do that is we're going to take theta and set it equal to its previous value, theta, times pi divided by 180. So we're basically redefining what it's equal to, because this theta is referencing this right here. Theta is equal to 30, and it's reassigning the variable to something new. And so now we set our variables, and we're going to now move on to finding our forces, which we are also going to be doing by finding a bunch of variables. First, we're going to start with the force of gravity, which is equal to negative, because it's pointed down, m times g. Then we're going to find our components of gravity. Fg parallel is equal to, once again, negative, which makes it positive, because previously we defined that positive is the direction going down the ramp, parallel to it. And so we need to make it positive. Fg times sine theta. Then we're going to do the same. Fg normal, because I don't want to have to type out perpendicular every time, is equal to Fg times cosine of theta. And in this case, it is going to remain negative because the normal component of gravity points down from the perspective of the ramp. Then our normal force is going to be equal to negative Fg normal, which makes it positive because it's pointing up from the perspective of the ramp. Once again, just how we defined it. And then Ff is equal to mu, once again, negative mu times Fn.
because in the problem, we defined that as being up the ramp, which is negative. All right, so now we have all of our forces defined, and we just need to add them together to find F net. So F net is equal to FG parallel plus FF, because those are the two forces that are acting on it in the parallel dimension, parallel to the ramp. All right, so now that we found F net, we just need to go ahead and find and print it out to make sure that everything is in working order. All right, and so what's going on here? F net right here is a number. Specifically, it is a float, which is a number that has decimals on it. Different from an integer, which is no decimals, as I'm sure you know. But the print function, which we have right here, only affects variables which are of the string type. Otherwise, it's going to give you an error message. So what we need to do is we need to make fnet into a string. And we do that using the string function right here, which we just feed fnet into. And then if we go ahead and print that, we get fnet, which if we went through and calculated this, I'm sure that's what it would be. And that's, of course, in the direction down the ramp. All right, so I'm going to go ahead and delete that because we don't need it anymore. And then, so we have fnet. Now we need to find the net acceleration, which is just using second law. Fnet is equal to ma divided by m. A net is equal to fnet divided by m. All right, and so now we have our net acceleration. Now we can finally go ahead and feed that into our position function. So we're going to define a variable d is equal to 1/2 times a net times a variable t squared. All right, and what you'll notice here is that we have not defined the variable t before. We've never seen a t before. So if we tried to run this right now, it's going to give us an error message because we've never defined t before. So we're going to define it right here, and we're just going to give it any old number, really. Let's say 2. And so what this will give us is the displacement down the ramp after 2 seconds. And then we're going to print this just to make sure that it is all well and good and that we can actually see what our displacement is. And if we print 8.10259. All right, so that is the displacement down the ramp. And then if we go ahead and check that with the equation we found earlier, which is 1/2 times g sine theta minus mu cosine theta t squared, we can see if that is accurate. So we're going to do that real quick. Minus. And I don't know about you all, but I am getting 8.10259. So perfect. You love to see it. All right, and so we have just basically solved this problem in Python. It didn't take long at all. But I feel like there's a little bit more we can do. So we're going to try something different. For one, we're going to import some new functions from different libraries. This one is going to be import matplot lib.pyplot as plt. And what this is basically doing is it is importing the plot function as with plt as the indicator of that. Then we're going to do the same, import numpy as np, and the as right here is basically saying what we are going to call this function as whenever we need to use it. And so np is what we're going to be calling it for numpy, and plt for plotting. All right, and so first, let's go ahead and find the x and y components of displacement, because I think that would be quite interesting to know. So what we're going to do is we're going to have x comma y is equal to, and then we're going to have d times cosine of theta, and then comma d times sine of theta. And if you're familiar with how vectors work, this is basically the same function, or even ordered pairs. We have x right here is being assigned to the first item, and y right here is being assigned to the second item. So it's basically just assigning two variables simultaneously. And if we go ahead and print out x and string of y, we can see both of these. And if you do Pythagorean theorem with that, we should get this number right here, ideally. We're going to get rid of that for now. All right, but here is what we're going to do now. We are going to try graphing it. That is the goal here. And that's why we imported these right here. And so how we're going to do that is we're going to need to create a list of t values. So to do that, we're going to do np, which is calling numpy right here, dot linspace, which is the function. And then we're going to create an array of t's starting at 0, ending at 5, with a total of 500 items in that list. So for every second, we're going to have 100 points, which sounds pretty precise to me. And then we're going to, again, do the same function for d as we did up here. We're going to have 0.5 times a net times t times squared. And because t here is an array, that is going to be applying this d to every single value in the array t. And so d will also be an array made up of 500 data points. And if we want to see that, then we can print out d for ourselves. And we get 500 data points of d. But that's a lot to look at, so let's not for the time being. But now we have d, x, and y. And once again, you'll notice because x and y are both being set to basically a function of d, they are also going to be similarly arrays of 500 data points, which range from 0 to 5 seconds. All right, so now we have our arrays. All we have to do now is to plot them. And so we're going to do plot, or plt dot plot t comma t, and then label is equal to t versus d. All right, and this is basically creating a plot where on the x-axis, the first number, we have t, and on the y-axis, we have displacement. And then our label for that line is going to be time versus displacement. And then we're going to label both of our axes. So we're going to label x, and we're going to label y, which is going to be d. And if you'll notice here, all of our things which are strings are in quotations, which is how you denote that. And then we're going to title it, which is plt.title displacement over time. And then we're just going to show our legend as well, because why not? And show our grid. And then finally, we're just going to show the graph itself. And then if we go ahead and run this, we get a beautiful graph right here, which shows displacement over time. And as you can see, this is from 0 to 5 seconds. So if we let it roll down that ramp or slide down that ramp for that long, it's gonna roll a good 50 meters. But we're not gonna do that. We're gonna just do it for, let's try it for 2 seconds and see how far that gets us. And it should get us 8.1 meters. And if we see, yep, just a little over 8.1 meters, just as we thought it would. But we don't have to stop there, because if you'll remember, we plotted both x and y as well. So what if we just want to see the x component of its displacement over time? What is that going to look like? It should also look like a parabola here. because x and y are both just scaling factors of d. And so to do that, all we have to do is change this variable to an x, this variable to an x, and then this variable to an x. And then we can just call this x, displacement over time. And then if we run this, now we have the displacement in the x, which if you remember from when we tried it out earlier, the x and y components, x was around 7. And we can see that still holds true here. And of course, we're going to do the same for y, just to try it out. And it's a little over 4, which is just what we calculated. And then let's just try one more here, which is x versus y. And if you think about it, this should just be a straight line because it is rolling on a ramp. So it really can't go much farther than that, because it's going to stay locked on its path. So we're going to say x displacement versus y displacement, because we have x in the x and y in the y. If we run this, we can see it is a straight line, which is going in the positive x direction and positive y direction. But we know just intuitively that it is actually going down in the y direction. And we can actually change that here if we wanted to by making that negative right there. And there you go. And so this is basically how you problem solve in Python. You use the same things that you did with on paper. And you assign everything you need to variables. You import what you need from the libraries that you need them from. And then you basically just do math using Python. And you do it in these little concise cells like this. There's a lot more you can do. Like we didn't get into defining functions, creating objects, object classes in here. But for just, a little simple problem like this was perfectly fine. And, I think our graph turned out quite well and we gained a lot of information from it. So it was overall a success, I'd say. So thank you all for coming, and I hope you choose to tune in if I decide to make any more of these videos. So thank you so much for joining us, and this will be all for today. Bye.